Our topic for today is finding the vector sum using the component method. Now, as we learned in our part 3, we have analytical method using cosine law. So we are able to find the vector sum. So in this video, let us discuss another method of finding the sum, which is the component method. So let us recall first the cosine law, sine law method of finding the vector sum. So in part 3 of the video, we learned that the cosine law and sine law can be used if we have the triangle. So in order to form a triangle, let us connect these two forces into two polygons. So we have to decide a point, then we have to reconstruct this F1, then connect the F2 at the tip of the F1 so that we have this tail-tip combination. So since we have the two forces, the closing point is the closing line is the resultant or the vector sum. So in previous video, we learned on how to calculate this because we introduced the cosine law for the magnitude, and we also find the direction using the sine law. Okay, so in other words, it depends upon our ability on providing the solutions of an oblique triangle. So we use the cosine law is actually taken from because these are given, two sides are given, so this angle also is given. So we have the two sides and one included angle. So therefore, we simply solve this resultant using the law of cosines. So we find it very simple because we have only two forces. Now, question is, what will happen if we have three forces? Can we apply the cosine law? The answer is yes. Any number of forces finding a vector sum, we can use this cosine law. But the problem is, we will encounter the more forces we have to find the vector sum, the more difficulty encountered during the process. So anyway, so let's do it. So first, again, construct the polygon, the tail-tip combination. So we have to decide F1, or you can start at F2 or F3. It doesn't matter as long as you have to connect all the forces, given forces, the magnitude and direction should be reflected. So okay, next we have to connect the F2 or F3 at the tip of F1. So we have to construct the Cartesian tip, then construct this force. Okay, then overlay again the Cartesian at the tip, then connect the F3. So these are the tail-tip combination of the vectors. These are equal vectors to the given. So therefore, in order to close the polygon, you have to connect a line from the beginning to the end, and this will serve as our resultant. Okay, now how will we solve this one? To solve this resultant, then you have to divide this quadrilateral into two triangles. Okay, so you have to connect this point to this point so that we have this triangle. So by triangulation, in order to solve for R, you need to provide the information of this line, because this line is the vector sum of these two, just like what we did before. This is the vector sum of F1 and F2, and we can find this angle as the direction of the vector sum. So after calculating this triangle, we have to consider again this another triangle using the calculated vector sum of this side. Then you can now solve for the resultant and also with the direction. So therefore, you have to do the step by step. First, use this triangle, then after this, use this triangle. So you have to start from 1 to number 2 triangle. You cannot start at this triangle because there are two informations required. So we have only one. In this case, we have two informations, two sides, and we have this angle. So therefore, you have to start at this, then use the calculated to solve for R. Okay? I think it's okay. It's more difficult compared to the, because we are working with two triangles. This is for three forces. Now, what will happen if we add more forces? What do you think? Okay, the same. Connect the first, then the second, then the third, then we have to add this one, A4. So then, that's it. Then your R will be the closing line. So therefore, what will you do? Actually, if this is drawn to scale, this is now a polygon method. So you have to construct those. But in this topic, we will solve this using analytical method, using formula. So in order to solve this one, then if you wish to use this method, then divide this into triangles. So we have the first triangle, which connect from the starting point towards the tip of the second force. Then after that, find this one, the vector sum of F1 F2. Then after that, cut this one. We have another triangle. So you have to solve this one. This is the vector sum of these two vectors. Then find the angle. Then after that, finally, you have to create this triangle, then solve for R. That's it. So you notice the increasing difficulty as the number of forces increases in finding the vector sum. So it is not advisable to use actually three or more forces. It is not advisable to use this method. Okay, so the question is, what is the method we use? For three or more forces, the applicable method is the component method. So we will discuss today on how component works on this problem. Now this method is very simple as long as you know the process of, or the steps of finding the vector sum using the component method. Okay, so let's start. Analytical component method. So suppose I have this object again. Suppose this object is subjected by a force. So we have the vector A and we have the direction. Now if you use the component method, then from the name itself, the method uses the component, and the components are the components of the vector. So if we have vector A has components. Okay? Now the components are depending on the number of the axes. So in this case, we have only two axes. So we have the X and Y. So therefore, we have two components along X and along Y of this vector. So the method uses the component, not the vector. So the question is, what are the components? How will we construct a component, and how will we compute? We need to compute the components using the vector and its magnitude and its direction. So the components are actually constructed from the tip of this vector projecting towards the x-axis. If you construct a vertical line until it reaches to this x-axis, okay, and connect a line horizontally projected towards y, okay, then we have this intersection point. We have two intersection points, and these are the tip of the components. This is the tip of the component along x. So therefore, you have to construct a line, and take note, the component of a vector is also a vector. So ax is also a vector. So we have the arrowhead. This is component along x. So this is the tip, and the tail starts from the origin. So therefore, your y is also towards the intersection line. So the end of the components are the projected lines, vertically and horizontally. So this is it. We have these two components. Okay? So we need to know the components, the magnitude of the components. And that's the process of component method. So therefore, we will discuss first on how to compute the component. Then after that, I will give you the steps on how to compute vector sum using component method. Very easy method. Okay? So, in order to solve for these components, we need to use the polygon. Take note, it's concurrent of forces. So we can create a polygon out of these three vectors. 1, 2, 3. Vector A, the x component, the y component. So do it the same in our previous. You have to decide, okay, the point. So we will construct the equal vector EX, then connect this y component at the tip of the x. So we have to connect this one to this tip, okay. Then you have to construct this A2 or vector A. So the vector A coincide the tip of the if these are the components of EX, so therefore surely this vector should reach at the tip of the EY. So therefore this is forming a kind of right triangle. So if we express this vectors in terms of each component, this should be the arrangement. The vector A, which is this one, is the vector sum of its component. Take note, this is vector sum. So it should be EX plus AY. Now reminders that this plus sign is not an arithmetic sum. This is a geometric sum. Remember in our previous videos, arithmetic sum is different from the vector sum. Okay? Because it involves angle. So in this case, the angle is theta. So we cannot add actually AX and AY because this is vector sum. Okay? So therefore, these are the components. Now the question is how to calculate the components along X, along Y using the magnitude and using its direction, because given the magnitude, given direction, so how will we compute? To answer is, use this triangle. This is a right triangle, so we can apply the trigonometric functions, the cosine and sine. If you notice, this is given and this is given. Okay? And take note, this is always 90 degrees. So there are three informations in the triangle given. Take note that in order to provide a solution to any triangle, there should have three given informations. In this case, this is already 90, so we have these two. So therefore, we can solve we can solve the sides. Okay. So if you take the opposite over hypotenuse, that's sine. So therefore, we are solving AY. And if we take cosine, cosine is adjacent over the hypotenuse. The hypotenuse is the vector A. So therefore, do it. Take the cosine. It is adjacent over hypotenuse. So this is given A and this is given theta. So therefore, EX must be A cosine theta. Okay, then AY is opposite. So therefore, it should be sine AY over A. Then take the diagonal product. AY is equal to A sine theta. Okay? So therefore, this is the formula. You can use this formula for the x component. Use cosine. Use for the y component. Use sine. Provided, okay, provided you're allowed to use this one. Provided that the angle is adjacent to the x. Because if x is adjacent, if AX is adjacent to the angle, then it should be cosine. In other words, if the angle is adjacent to y, then the y function, the y component should be cosine. Okay? So in order to make in order to have an idea on how to use cosine or sine, now take note that the angle should be coming from x. So take note that an angle coming from x, an acute angle, is called reference angle. So in order to have a safe solution, engage your angle or express your angle in terms of the reference angle. So that if that angle is a reference angle, you have to use the cosine for the x component and sine for the y component. Now remember, these vectors components are vectors. So therefore, there's magnitude and we have the direction. In this case, the magnitude is A cosine for EX, A sine for AY. And the direction is, look at the direction. The direction is towards the positive x. So therefore, this should be positive. And this is upward. So therefore, this must be positive. So this is, take note, this is located in the first quadrant. Which means to say, if this vector is located in the second quadrant in this point, so therefore the ax component is negative while ay is plus. In the third quadrant, all components are negative. In the fourth quadrant, ax is positive, ay is downward, so therefore negative. Okay? So it's very important to know the direction of that component because the components are lying on the axes, so the direction can be expressed in terms of algebraic sign. Okay, so then this, in order to double check if your answer is correct, then you can take the square root because this, take note, this is right triangle, so we can apply the Pythagorean theorem. So this is the Pythagorean theorem formula. You have to square the side, another side square, then take square root, the answer is a, and you will arrive the same answer. Okay, then in order to solve this one, the angle or double check, then you have to use tangent because tangent is opposite over adjacent. Then take the inverse, then it should be ay over ax. Why ay? Okay, ay, so that your angle is a reference angle. So therefore, if you reverse this one, ax on the upper and ay in the lower, then you are computing the angle adjacent to y. So this is a reference angle. Okay, so this process actually, you can use this process if the components are given. So but in this case, the vectors and its magnitude of the vector and its directions given, then you can solve for the components. This process is called as the resolution of vectors. We are resolving the vectors into its component. This process is composition of vectors. We have two processes, the resolution of vectors and we have the composition of vectors. Okay, so actually the process uses only the simple mathematics. Okay, so we have now the idea on how to compute the component, because it's in the component method you should know the components of all vectors because we will be working with the components. Okay, so therefore let's proceed to the steps in component method. So for example, we have two forces drawn not to scale, no need to scale because this is analytical method. Okay, so then suppose I have this force F1 and we have this angle direction theta, another force F2 and the angle is beta. Suppose we are asked to solve for the resultant and use the component. So step 1, first is to resolve the vectors into its component. So you have be sure to have the idea. Now take note the components in our previous slide. We understand that the value of ax is cosine times the magnitude of the vector, then sine for the y. Okay, provided that this angle is reference angle. If not, you have to reverse the trigonometric sign. Okay, so in that case, this is the component, diba? You have to construct a vertical from the tip downward projected towards x. So the intersection is the x component of f. Now take note, this is negative y because this is towards the negative x axis. And the y component is constructed at the tip, projected horizontal line towards the vertical axis. So therefore, your y component must be in this direction. So the components of F1 is towards negative and the y component is towards the positive because this is second quadrant. Okay, so the other force F2, then we have the F2x projected the imaginary line, then we have this vector. Take note, first quadrant, so all components are positive. Okay, so we have two components on each forces. So all in all, we have 4 components. So all you need to do is to find this one. F1, use the cosine. So F1 times theta. F1 times cosine theta is the x component and it is negative. Then F1y cosine, use this angle. Now for the next force F2, use F2 x is equal to F2 magnitude times the cosine of beta. Then for the F2y, use sine. That's it. As simply as that. So therefore, next step is to sum up all. Okay? You have to sum up everything. All components along x. So you have to combine along x. What are the x component? We have the f1x and we have the f2x. You have to combine this algebraically. Now, there's a word algebraically because they are lying on the same axis. So no angle between them. So therefore, you can add this algebraically. So sum up along x and sum up along y. The y components are f1y and f2y. So therefore, from the left drawing, this one, you have to sum up along x. Components along x. So this is the word of summation. Or you can ignore this one. This is understood to be the x component. So see it rx. Okay, rx is the sum of all components along x. So we have this negative because this is according to the figure. This is towards left, so this must be positive, negative. If this is towards right, then this should be positive. This is algebraic. This is the meaning of algebraically sum up. So then f2x is positive. Now if we have another force here, then continue. Okay? So therefore, the component method can be applied to any number of forces. Feel it comfortable because you just use this formula, the a cosine theta and the a sine theta for the x and y components. But be careful of the sign convention. It's positive or negative. So the dot here signifies if there are more components. The number of forces or the number of components. Okay? So we have two components. We have the two components because we have two axes, so we have two components for every vectors. Okay? So then next is to sum up all forces along y. So we have this all positive because these are all upward. Again, depending on the figure. So that plus that means if there are other forces, then do it. So take note that this is the x component of the resultant already. Okay? This one, actually, we use the resolution of components. Finding f1 and f1x and f1y is actually resolution. Now in this case, look at this one. Rx is the component of the resultant. And this is the component along x, and this is component of resultant along y. So practically, we can calculate the resultant because the resultant is actually the hypotenuse of these two sides. This will serve as a side of the triangle. Okay? So therefore, look at this one. If you sum up this algebraically, this can be positive result depending on the numbers given, and this can be a positive. Also with ry, this can be positive or negative, but in this case, we are very sure that this is positive. But in other cases, this can be a negative or positive or zero. This can be also a positive number, negative or zero, depending on the. Now, what's the meaning of positive? So if Rx is positive, so it's understood that from the Cartesian, the x component is going to the right. If this is negative, it's understood that this Rx is coming from the origin towards the left. Now, for y, if positive, from the origin, upward. If negative, downward. Okay. Suppose the result is negative for Rx and positive for Ry. So, negative Rx. So, if this is negative, Rx negative, your Ry is upward. So, therefore, the resultant is found in the second quadrant. Okay? So, very important the sign convention of the resulting components because it signifies the location of your resultant. So, to compute for R, you can use the by the way, these are the components. So, use the cosine. That's the reminders. Cosine because we have this as the reference angle. If not, then convert that to reference angle. Okay? So these are the components of the resultant. So next is to calculate now the magnitude. Given this 2, we are now ready to calculate the magnitude and direction of the resultant, the Rx, and you have the Ry. So to do it is to use the Pythagorean theorem. Remember in our previous slide, we have this square root. Why? Because this is the, actually R is the hypotenuse side. So we actually use the Pythagorean theorem. Okay, then substitute it here. Now when you square this one, even if this is negative or positive, it doesn't matter. Because when you square it, this will become positive. So R magnitude provides always a positive. There's no negative magnitude of the resultant. It's always positive. So ignore the sign. Okay? So then calculate. Then that's the magnitude. Now the direction is, remember tangent in our previous slide. So use the, I have this symbol for the direction of the R. Gamma is inverse tangent of Ry over Rx. Take note, Ry over Rx, and the result, the angle is coming from the x-axis because denominator is the reference point or line. So therefore, this is the direction of the resultant. Okay? This is it. This is the method or the steps of finding the component, the resultant using analytical component method. Okay? So actually, we use the resolution for the components, and we use the composition because in this case we have these components of Rx, so we use the principle of composition in order to solve for R and its direction. Okay, so let's have the example. By the way, we can interpret, remember this one, we can interpret this in another way. This is actually using concurrent of vectors. What if the vectors are connected in a tilted condition? So therefore, if we have this F1, then connect the F2 at the tip of the F1, tail of F1 to the tip of F2, then we have this line. So the closing line, remember, is the resultant. Okay, so where is the resultant? So the resultant actually is coming from this tail to the tip, to the last force. So this F21 negative F1x is, F2x is this one. This is the F2x, the x component of F2. Now where is your F1x? The F1x is actually in this point. The F2y is upward. So F1x, F2x, and F2y, the y component, the x component of F1 is towards the left. Okay, negative, that's a negative. Then upward. Okay, so notice that, look at this one. If you sum up this F1 and F2, F1x and F2x, the result is graphically this one. Okay, so this is actually Rx. So from here to this point, which is in line approximately this point, is the Rx. So the Rx is towards the right. Okay, now what is Ry? Ry is actually the sum F2y and F1y. So therefore, your Ry is this one, from this point up to here, and the resultant is actually at this point. This is the resultant. So the resultant, the Rx is, look at this one. This is the Rx projected vertically downward. So this is your Rx, and this is your Ry at that point. Okay, so there are two interpretations. It can be in a concurrent of vectors, or it can be in a polygon type resultant. So take note, the concurrent can be converted into polygon in our previous video. So therefore, this is the another way to interpret the component method. So yep, you understand. So in order to make clearly, we'll have the example. So the problem says that find the magnitude and direction of the resultant using polygon method. Okay, no, you have to ignore the polygon method because this is analytical. So use only the sine law and cosine law method. in this case, because our topic is talking about the component, ignore this other method, use only the component. Now for your practice, I think it's good to go back our previous videos using polygon method, graphical, and you have the cosine law, then double check your answer of the component method. Okay, so step 1. Step 1 is to resolve the component into the forces into components. We have the forces 200 gram force in the direction of the direction is 30 degrees from x, while we have another force 400 gram force, and we have this 35 degrees. Then we have 500 gram force 65 degrees. So the 200 is located in the second quadrant, the 400 is in the third quadrant, while the 500 is located in the fourth quadrant. Okay, how much is the resultant magnitude and direction using component method? To answer is, we have to solve the magnitude of the resultant first. Okay, so solve for the magnitude r. So to solve for r, remember how to solve for r? We need the components along x and component along y. So first step, solve the x component, then y component. Now what's the x component? Now recall in our previous slide, the steps is to resolve all the component along x, then sum up, then that's the rx. Now for ry, resolve the forces into its component, then collect all the y. Okay, y component only, then sum up algebraically. Okay, let's do it. So I think it's good to use this method. Now look at this force. Okay, take note, we are concerned only the x component of 200 first, because we will solve for rx. So the component of 200 along x is what? Okay, or we'll start at this force for 500. So the component of the 500 along x is 500 times cosine. Remember, x component cosine, because this is reference angle. So positive, y positive, because this is towards the right. Okay, next, you can start any of these two forces. Okay, now take note, the x component of this is negative also, the same as the 200. So we have the 200 negative cosine of 30, so we use the component of 200. Then the component of 400 is again negative 400 cosine. That's it. Then use the calculator, and the answer is negative 289.56 gram force. So what does it mean? What's the meaning of negative? The meaning of negative is Rx is towards the left side. So very important. So therefore, because this is negative, so we are very sure that the resultant can be found in what? It's either quadrant 2 or quadrant 3. We have no definite answer whether to come up with quadrant 2 or quadrant 3, because we have only the idea of x. So the correct direction of that r depending on the value of y. If it is positive, so therefore the resultant is located in the second quadrant. If this is negative, this is the resultant is located in the third quadrant. Okay, so straight for the y. So the y component, the 500 is sine. So this is downward. So therefore this should be negative 500 sine of 65 degrees. Now for the 200, this is upward. Okay, take note of the component. Upward, because this is the tip. Project here. The upward is the y component. So it should be plus 200 sine of 30. Now what about 400? This is located in the third quadrant. All components are negative because it's negative. So therefore this is also negative. But take note, this is cosine and this is sine. And calculate, and the answer is negative. So what does it mean? The r is downward. So therefore the resultant is somewhere in the quadrant 3. We are now very sure that is located in quadrant 3 because of this sign. So, be careful with the sign, algebraic sign, because it gives us the direction of R. So, again, we we use the cosine always because these are all reference angle. So, by the way, if the angle is not in reference, for example, standard, so what will you do? Now, if the angle is standard, okay, use it. Do not use the sign. For example, suppose I have 230 degrees. So, use the 230 degrees. Do not use negative, always plus, because the cosine of that angle will gives you the algebraic sign. So, we are careful to have the angle or the sign here because we use the reference angle. But if we have the standard, then no need to have this negative because your negative will be given during the calculation of your cosine. Okay? So the ideal one, I think, is transform that angle into a reference angle so that there is a uniformity and okay, then easy to see the components of that vectors. Okay, so next is what? This is Rx, Ry. So therefore, R now can be calculated and they use the square root in our previous slide. So then substitute the values. Do not include the negative sign again because we are now concerned with the magnitude. If you do it with negative, don't worry because when you square it, it will becomes positive also. But okay, so therefore, this is the R. More or less, this is the direction because your Rx is negative and your Ry is negative. So therefore, that's it. Substitute the values and we are calculated the result as 650.58 gram force. This is the magnitude. Okay, and for the direction, then we have by the way, the angle is this one. If you want the angle from X, then use the, again, Ry over Rx. This is Ry over Rx. Do not use the negative sign, okay? Because you cannot calculate the angle using the negative. There's no negative side in the triangle. And this is actually using the triangle. Okay, so ignore all the signs. But we understand that R is located in the third quadrant. So therefore, the calculated angle actually is this angle from the negative x in quadrant 3. So use the calculator and it's found out that this is 63.57 degrees. So is this enough to describe the angle? The answer is no. You have to specify something. This is from negative x and this is located in quadrant 3. This is the exact description of this angle. If you give only 63.57 degrees, we are hanging with this angle only. But because of this drawing, it's understood. But it is very complete solution if we have this information. Okay, so this is for this problem. Suppose we have the worded problem. Okay, the problem says we have the cross-country skiers case 5 kilometers in the direction of 50 south of east. So these are the skiers. So take note that the first direction is we have our first displacement of the travel is 500 is the length and this is the direction 50 degrees. This is south of east. What is south of east? South of east means this is the southern part of east. Okay, so when you start with your solution, first you have to construct first the travel of this activity. So the 50 means 50 south of east means this is the 50 degrees southern part of east. This is east. Take note. In east we have the southern part. So from here, this is the southern part, and we have the northern part. So therefore, this angle must be 50 degrees coming from east going to the southern part. Okay, so this is the meaning of 50 south of east. So then You have to connect a line from here, connect starting point, then we have the 50 degrees, then draw a line. Okay, so this is 5 kilometers of travel. So the skiers now is at this point. They started with this point, then this is now the second position. In the second position, according to this information, we have 3 kilometers. 3 kilometers in the direction of sorry, this is 60 degrees. No, there's no 600 degrees with north. The meaning of this is the north 60 degrees of east. Again, this is degrees, 60 degrees east. So this is different from north. This is angle is before, okay, of the, so this is 50 south of east. This is north 60 degrees east. Okay, so what is this angle? This angle 60 degrees is coming from the north. Okay, this is coming, if the angle is in between of the axis, okay, so north pole and the south pole, in between of the axis, so then the angle is coming from the north, or it can be from the south depending on the, so this one is the reference. So from north we have 60 degrees, and this is east. Okay, by the way, you are now in this position, so you have to construct the Cartesian or the north, south, east, west axis. So the angle is coming from north, so you have to construct the 60 degrees coming from north, because this is north 60 degrees east. So the displacement is coming from that line towards this line until traveling 3 kilometers. Okay, so then next is, you are now in the third position, so construct again the Cartesian or the north-south axis. So then in the third, this is the final travel, and finally 8 kilometers with a bearing angle. Is the meaning of bearing? The bearing angle is coming from the north. Okay, the bearing angle is coming from the north, moving in a clockwise direction. Okay, so therefore this is the bearing. So from north you have to construct 338, so approximately very close. So because the complete circle is 360 degrees, so this is the 338 drawn not to scale. So then construct a line that passes through that angle, and 8 kilometers of travel. So this is the final position of the skiers. So okay, 8 kilometers, 3 kilometers, this is 5 kilometers. So they started at this point, then traverse until reaches the final point. What's the question? By the way, reminders at the bearing. Okay, 338. If this is negative, then you have to reverse, because this is positive, so it should be clockwise. Standard angle is coming from the x-axis in the counterclockwise standard angle, but this one bearing is coming from north, clockwise direction. The question is find the displacement of scale. So from this point you have to connect a line. This is the displacement. So the displacement is coming from the starting point. You have to connect it to the end point. So that's it. This is the displacement, and call it D as the displacement. So how will we solve this one? Using component. Okay, remember there are many methods of solving this one. You can use cosine, you can use polygon, you can use the parallelogram, but the simplest way to solve this is the component method. Okay, so how? Okay, how is, take note, we have these three vectors, 1, 2, 3. Then there are the components. So first thing is to solve for the x component of dy. So the x component of dy is towards this axis, towards S, and your y component is coming from this towards the end point, and this is vertical and this is horizontal. So these are the components of the displacement. So in order to solve this one, take note, this is right triangle, you have to provide the dx and dy. So to solve it is to, by the way, the angle must be calculated also as gamma from this axis. So all you need to do is to solve first the x component, because if we have the x and y component, then this magnitude of displacement and direction can be calculated using. Now remember that we will be working with angles now. So okay, so we need, because this is 60 degrees, so we have to provide the reference angle to make it convenient. This is already reference angle, and this is 60, so we have to use 30. In this case, what's the reference angle of 338? 338 minus 270. That's the 68 degrees. So we will be using the reference angle. 50 is already reference. Then do not use 60, so that it will be in a uniform of cosine for the x. This is 30 degrees and this is 68 degrees. Although you can use 60. If you insist to use 60, do not use cosine for x. Use the cosine for the y component. Now this one, there's also, you can use also 338 degrees. Do not use positive. Do not use negative or positive, because you substitute directly with the 338 to the cosine. So the answer will give you the algebraic sign. Okay? So for this solution, we will use the reference angle. So first is the x component, dx. So dx now is what? We'll start at this 50, or the 5 kilometers. So it should be 5 kilometers cosine use. Okay? So that's it. Positive because this is towards right. Then next, the 300 kilometers, use the 30 degrees. Again, positive. Okay? Then finally, this 8 kilometers, the x component is negative. So, negative 8 kilometers cosine of 68. That's it. Then calculate. The answer is 282 kilometers. And this is positive. Yeah, this is positive, dx. This should be positive. And the result says positive. Okay? Then y, what is y? Y is, start with dy, so the y component of the 5 kilometers is sine. So therefore, change this to, by the way, this is below this point. So therefore, the y component should be negative. Okay? So negative. Then, proceed to the second component. The y component of this is first quadrant. Okay, this is in first quadrant, so therefore it should be positive because upward. So 3 sine of 30 degrees. Then the 8 kilometers has the component of upward also. It should be positive 8 sine of 68 degrees. Then calculate. So we have 5.09 kilometers. Okay. So that's it. We have already the x component and the y component. Then we are now, actually, we are very near to the solutions of the solution problem. D is the resultant or the displacement. Take square root of this, sum the square, Pythagorean theorem. So therefore, the answer is 5.82. This is the magnitude of the resultant. The direction is gamma. Use the inverse tangent, inverse tan of y, dy over dx. And the answer is 62. Is this enough? No. This is what? Take note, this is the displacement, the tail and the tip. So therefore, this is in the region of northeast. Okay? So the angle can be 61 because this is the northern part of, so this is 61 north of east. Or you can solve this angle. If you solve this angle, north, this angle is, but this is reference angle because this is along or divided by x component. So this should be reference. So use the north of s. That's it. That's the solutions to this problem. If there are more displacements, then continue. Then you have to add for x, add for y for every movement, then sum up, do it the same. Be careful with the positive and negative. That's the important part. Okay, so that's all. Thank you. Now, see you on my next video. The